What if alien life isn't hiding on distant planets, but inside oceans beneath the ice of worlds in our own solar system? Right now, scientists believe several nearby moons could be hiding entire alien ecosystems. For centuries, we searched the stars for alien life. But the most promising places might not be distant galaxies. They might be frozen moons orbiting giant planets just beyond Earth. Worlds with vast underground oceans, chemical energy, and conditions that could support life today. In this video, we'll explore the mysterious worlds scientists believe could still be hiding alien life right now. The answer to one of the greatest questions in human history may not require a journey of thousands of light years. It may not even require leaving our own solar system. Because in the last few decades, as space probes have pushed deeper into our cosmic neighborhood and returned data that nobody quite expected, a picture has emerged that changes everything. Hidden beneath the frozen surfaces of several moons orbiting Jupiter and Saturn, there may be oceans. Not small pockets of liquid, not trace amounts of moisture trapped in rock, but vast, deep, planet-scale bodies of water sealed beneath ice crusts kilometers thick, sitting in permanent darkness, heated from below, quietly existing for billions of years without a single human eye to witness them. This is not speculation drawn from the edge of theory. It is the conclusion toward which decades of spacecraft data, gravitational measurements, and magnetic field readings have been steadily pointing. And when scientists began to grasp the full implications of what those instruments were telling them, the conversation about life in the universe shifted in a direction no one had quite anticipated. We had been looking outward for so long that we had failed to look sideways, at the worlds already orbiting the same star as us, already within reach of our spacecraft, already waiting. Consider what liquid water means. On Earth, it is the non-negotiable prerequisite for life as we understand it. Every organism ever discovered on this planet, from the most complex mammal to the simplest bacterium, requires it. Water is not merely a habitat, it is the medium through which chemistry becomes biology. It dissolves nutrients, enables cellular function, carries energy across membranes, and allows the molecular interactions that separate living systems from dead ones. Wherever liquid water has been found on Earth, no matter how scalding, how acidic, how pressurized, how remote, life has followed. Not sometimes, every time. And now science has found evidence of liquid water in places that should, by all intuition, be frozen solid. Europa, a moon of Jupiter, sits hundreds of millions of kilometers from the Sun, in a region of the solar system where temperatures plummet to nearly 200 degrees below zero. Its surface is a fractured shell of ice, cracked and refrozen countless times, scarred by stresses that only a vast body of moving liquid beneath it could produce. Scientists believe Europa's subsurface ocean may contain twice the volume of all Earth's oceans combined. Let that settle for a moment. Twice the volume of every sea, every ocean, every lake and river and underground aquifer on this planet, hidden beneath a layer of ice on a moon most people couldn't locate on a diagram of the solar system. But Europa is only the beginning. Enceladus, a small moon of Saturn, so reflective it shines like a polished pearl, has been observed actively venting water vapor and ice particles from cracks near its south pole. When the Cassini spacecraft flew directly through those plumes, it detected organic molecules, molecular hydrogen, and silica particles that could only have formed through hydrothermal activity, meaning hot water interacting with rock at the ocean floor, deep beneath the ice. Hydrothermal vents. The same geological feature that on Earth is considered one of the most plausible environments for the origin of life itself. On Earth, the discovery of hydrothermal vent ecosystems in the late 20th century rewrote the limits of biology. In environments of crushing pressure, complete darkness, and scalding mineral-rich water, entire communities of organisms were found thriving. Tube worms, microbial mats, shrimp with no functional eyes, chemosynthetic bacteria, drawing energy not from sunlight but from chemical reactions. Life, it turned out, did not need the sun. It needed chemistry. It needed energy gradients, mineral exchange, and liquid water. Enceladus appears to have all three. This is the realization that reframes everything. The search for life has always been anchored, consciously or not, to the assumption that proximity to a star is the primary requirement. That habitable zones are defined by surface temperature, by the right distance from the right kind of sun. But life, at least on Earth, never received that instruction. It found every crack in the rule, every chemical shortcut, every dark and pressurized corner where energy could be extracted and survival made possible. If Earth's extremophiles, organisms living in Antarctic subglacial lakes, sealed under ice for millions of years, in sulfuric hot springs, in the acidic interiors of volcanic craters, if these forms of life can endure conditions that would destroy most biology, then the environments inside Europa or Enceladus are not impossibly hostile. They are, by comparison, familiar. The question, then, is no longer whether the conditions for life could theoretically exist on these worlds. The data increasingly suggests they do. The question is whether life actually arose there, and whether in those dark and pressurized oceans, billions of kilometers away, chemistry crossed the threshold into biology. Whether something is moving in the water, whether ecosystems are evolving in total isolation, completely unaware that another living world exists on the other side of the ice, and whether in this generation or the next, humanity will finally develop the means to reach through that ice and find out. The conditions required for life are not as rare or as distant as we once believed. What remains unknown is whether those conditions were ever enough. For most of human history, the definition of a habitable world was simple, intuitive, and almost entirely wrong. A planet needed to be the right distance from its star, close enough for liquid water to exist on its surface, far enough not to be scorched into sterility. It needed sunlight because sunlight meant photosynthesis, and photosynthesis meant energy, and energy meant the possibility of complex chemistry building towards something alive. The habitable zone, scientists called it, the Goldilocks zone, not too hot, not too cold. Just right. It was an elegant framework, and it shaped the entire direction of astrobiology for decades. There was only one problem. Life on Earth never agreed to follow it. The deeper scientists looked into the most extreme and inhospitable environments on this planet, the more consistently they found something they hadn't expected to find. Not absence. Presence. Life, in forms that had no business surviving, not only persisting, but thriving. In boiling acid pools in the frozen cores of Antarctic glaciers, in the irradiated soil surrounding nuclear disaster sites, in the crushing darkness of the deepest ocean trenches. Each discovery forced a quiet but significant revision to the working theory of what life actually requires. And when those revisions accumulated into a coherent picture, what emerged was not a narrowing of possibility but a radical expansion of it. To understand why, it helps to strip the question down to its foundations. What does life actually need? Not what Earth life prefers. Not what seems comfortable or familiar. What does life at its most fundamental level require in order to exist? Three things emerge with consistency across every living system ever studied: liquid water, a source of chemical energy, and the essential molecular building blocks, primarily carbon, nitrogen, hydrogen, oxygen, phosphorus, and sulfur. Remove any one of these three pillars and biology stops. Maintain all three in any configuration, under any conditions, in any environment. And life, the evidence increasingly suggests, finds a way. Liquid water is the most critical. Its properties as a solvent are unmatched by any other known substance. Water dissolves an extraordinary range of compounds, allowing the chemical transactions that underpin all known biology to occur. It remains liquid across a temperature range wide enough to accommodate enormous chemical diversity. It moderates temperature, stores energy, and provides the medium through which every cellular process operates. Without it, the molecular machinery of life, the enzymes, the membranes, the genetic material replicating itself across generations, simply cannot function. This is why the detection of liquid water anywhere in the universe is treated as one of the most significant signals a scientist can receive. Not because water guarantees life, but because without it, the conversation ends before it begins. Chemical energy is the second requirement, and this is where the story becomes genuinely surprising. For most of scientific history, energy meant sunlight. The photosynthetic pathway, light absorbed by pigments converted into chemical energy, stored in molecular bonds, was so dominant on Earth's surface that it seemed like the only viable route. Every food chain began with a plant or an algae or a photosynthetic bacterium, capturing solar energy and building organic molecules from it. Everything else ate those organisms or ate the things that ate them. The sun was the engine. Remove the sun, and the engine stops. This seemed not just true, but obviously necessarily true. Then in 1977, a team of oceanographers lowered a submersible into the waters off the Galapagos Islands, descended to a depth of roughly 2.5 kilometers, and encountered something that rewrote the foundations of biology. On the floor of the Pacific Ocean, in total darkness, under crushing pressure, at temperatures that exceeded what most organisms can survive, they found life. Abundant, diverse, structurally complex life. Communities of organisms clustered around cracks in the seafloor, where superheated water laced with dissolved minerals and chemical compounds was venting upward from the geological interior of the planet. Hydrothermal vents. And around those vents, as though the darkness and pressure and heat were entirely irrelevant, entire ecosystems had assembled. What those ecosystems ran on was not sunlight, it was chemistry. Chemosynthetic bacteria, microorganisms capable of extracting energy from the chemical reactions between the vent emissions and the surrounding seawater, formed the base of the food chain. Hydrogen sulfide, a compound toxic to most surface life, became fuel. Methane, iron, and other reduced compounds poured from the vents, and bacteria metabolized them, producing organic matter, building biomass, creating the foundation upon which everything else could feed. Giant tube worms, some exceeding 2 meters in length, anchored themselves to the vent structures and hosted chemosynthetic bacteria inside their own bodies in a symbiotic relationship, so complete that the worms have no digestive systems of their own. Ghostly white crabs picked through the microbial mats, Translucent shrimp clustered in dense clouds around the vent openings, some equipped with heat-sensing organs on their backs instead of functional eyes. An entire biological world, constructed entirely without reference to the sun, thriving in conditions that had once been considered definitionally incompatible with life. The scientific implications were immediate and profound. If sunlight was not a prerequisite, if the only true requirement was energy, in any form that biology could learn to access, then the habitable zone concept was not wrong, so much as it was dramatically incomplete. It described the conditions for surface life, for life like the life we see every day. But it said nothing about what was possible in the dark, in the deep, in the geologically active interior of a world where liquid water and chemical gradients could exist entirely independent of the nearest star. The discovery did not just expand the definition of a habitable environment. It demolished the previous one and replaced it with something far larger. In the decades following that first vent discovery, oceanographers found more of them. In the Atlantic, in the Indian Ocean, in the Arctic, scattered across the global seafloor wherever tectonic activity creates pathways for geothermal heat to interact with ocean water. And at every site, life. The specific organisms varied. The chemistry differed from vent to vent. But the pattern held. Wherever the three conditions converged, liquid water, chemical energy, essential elements, biology found purchase. The rule appeared to be universal, or at least universal enough to demand that scientists take it seriously as a framework for thinking about life elsewhere. The organisms that populate these extreme environments belong to a broader category that scientists have studied with increasing intensity. Extremophiles. The name simply means organisms that thrive in extreme conditions, and the range of extremes that different species have adapted to is, by any reasonable standard, astonishing. Thermophiles live and reproduce at temperatures above 100 degrees Celsius. Psychrophiles metabolize and grow in environments well below freezing. Their biochemistry adapted to function at temperatures that would solidify the cellular machinery of most life. Acidophiles thrive in environments with pH levels close to battery acid. Halophiles flourish in salt concentrations so high that ordinary cells would lose all their water and collapse. Pisophiles live under pressures hundreds of times greater than atmospheric, at the bottoms of ocean trenches where the weight of kilometers of water above them would instantly crush unprotected human tissue. Each extremophile represents a proof of concept, not a prediction, not a theoretical argument, a living demonstration that the boundary conditions for life are far wider than they appear from the surface of a temperate planet, with a mild climate and a conveniently positioned sun. Some of these organisms do not merely tolerate their extreme environments, they require them. Bring a thermophile into room temperature conditions and it dies. Its biology is calibrated for extremity. The extreme environment is not where it survives despite its conditions. The extreme environment is home. What this means for the search for life beyond Earth is difficult to overstate. For decades, the instinct was to look for Earth-like worlds. Similar gravity, similar atmospheric composition, similar distance from a similar star, similar surface temperature. The logic was straightforward. Earth produced life. Therefore, Earth-like conditions produce life. But the extremophile record suggests something more nuanced and more expansive. Life does not require Earth-like conditions. Life requires the three foundational ingredients, combined in any configuration that allows chemistry to function. Sunlight is one source of energy, but only one. Geological heat is another. Chemical gradients between different mineral environments are another. Radioactive decay in deep rock can drive chemical reactions that sustain microbial communities kilometers underground, sealed from the surface, isolated from the sun, surviving on energy released by the slow disintegration of uranium and potassium in the surrounding stone. The picture that emerges from all of this research is not of life as a fragile, improbable accident that required a perfectly calibrated planet to occur. It is of life as a chemically robust phenomenon, one that, given the right ingredients, appears with tenacious consistency across an extraordinary range of physical conditions. Life on Earth has colonized every environment it has encountered where those three conditions meet. Hot springs and frozen lakes, acidic craters and alkaline vents, the upper atmosphere and the deepest subduction zones. It has done so not because it was designed for those environments, but because the underlying chemistry of life is in some fundamental sense more flexible than we gave it credit for. And now, with this understanding accumulated and tested and confirmed across decades of deep-sea exploration and extremophile research, scientists have turned their gaze back outward, not to the distant stars, but to the frozen moons orbiting the giant planets of our own solar system. Because those moons, as the data from planetary spacecraft has made increasingly clear, are not barren and dead. They are geologically active. They are chemically rich. And beneath their frozen surfaces, they may hold oceans that have been liquid for billions of years, waiting in the dark for the chemistry that could turn them into something more. From a distance, Europa looks like a world that has already surrendered. Its surface is bright and featureless at first glance. A sphere of ice reflecting sunlight in the cold dark beyond the asteroid belt, one of dozens of moons orbiting the largest planet in the solar system, unremarkable in scale and seemingly barren in every visible sense. There is no atmosphere worth measuring. There are no rivers or mountains or volcanic plumes visible from orbit. The temperature at the surface hovers near negative 170 degrees Celsius. By almost every surface level indicator, Europa appears to be exactly what it looks like. A frozen, lifeless shell drifting silently through the Jovian system, geologically dead, biologically irrelevant. But appearances, in planetary science as in most things, are frequently the last reliable guide to truth. Look closer, and Europa begins to reveal something extraordinary. Its surface, rather than being smooth or cratered, like a geologically inactive world, is covered in a dense, intricate network of lines. Cracks and ridges and fractures running for hundreds and sometimes thousands of kilometers across the ice in overlapping patterns that resemble nothing so much as the surface of a shattered eggshell slowly reassembling itself. These features, called lineae, are not the result of impacts or ancient volcanic events frozen into the crust millions of years ago. They are dynamic. They form, shift, and reform over timescales that are geologically recent. Some regions of Europa's surface appear to have been completely resurfaced. Old terrain, disrupted, and replaced by new material welling up from below, as though the surface is being continually renewed by some process operating beneath it. For a moon this small and this far from the sun, this level of geological activity should be impossible. The question of what is driving it leads to one of the most dramatic discoveries in planetary science. The answer is Jupiter. Europa orbits the largest planet in the solar system, at a distance close enough that Jupiter's gravitational field exerts an enormous tidal force on the Moon's interior. As Europa moves through its slightly elliptical orbit, the gravitational pull it experiences from Jupiter changes. Stronger when closer, weaker when farther. This variation flexes the Moon's interior in a continuous cycle, generating frictional heat deep within its structure in a process called tidal heating. It is the same physical mechanism that makes Europa's more volcanically active sibling, Io, the most geologically restless body in the solar system. On Io, tidal heating is so intense that the Moon is covered in active volcanoes and sulfurous lava plains. On Europa, the effect is more subtle, but its consequences are, in their own way, equally profound. The heat generated by tidal flexing is sufficient, scientists believe, to maintain a layer of liquid water beneath Europa's frozen outer crust. Not a thin film, not a localized pocket of slush. A global ocean, a continuous body of liquid water extending beneath the ice across the entire surface of the Moon, estimated to be between 80 and 170 kilometers deep. For comparison, the average depth of Earth's oceans is less than 4 kilometers. The deepest point in any ocean on Earth, the Challenger Deep in the Mariana Trench, descends to just under 11 kilometers. Europa's hidden ocean, if the current estimates are correct, may contain roughly twice the total volume of liquid water present across the entire surface of Earth. A world smaller than our own Moon, floating in the frozen outer solar system, harboring more water than all of Earth's oceans, rivers, lakes, and glaciers combined. The implications of that single fact take considerable time to absorb. What makes Europa's ocean scientifically remarkable is not merely its size, but its suspected longevity. Tidal heating from Jupiter is not a recent development. It has been operating on Europa for billions of years, possibly for nearly the entire age of the solar system. This means the ocean beneath Europa's ice may have been liquid, not for thousands of years or millions of years, but for billions. That duration matters enormously when thinking about the possibility of life. On Earth, the earliest evidence of microbial life dates back approximately 3.5 billion years, and the underlying chemistry that led to life may have begun even earlier. The window required for life to emerge, whatever that process involves, is measured in hundreds of millions to billions of years. Europa, if current models are accurate, has had a liquid ocean for exactly that duration. Sitting quietly beneath its ice, chemically active, energetically driven, accumulating the complexity that biological origins may require. The composition of that ocean is another critical consideration. Observations from the Hubble Space Telescope and the Galileo spacecraft, which orbited Jupiter from 1995 to 2003 and made multiple close flybys of Europa, have revealed that the Moon's surface contains a range of minerals and salts that appear to have been cycled up from the ocean below. Magnesium sulfate, sodium chloride, and various organic compounds have been identified in the ice, suggesting that the ocean beneath is not pure water, but a chemically rich brine, potentially similar in some respects to Earth's own oceans. This matters because chemistry in pure water is limited. It is the dissolved minerals, the salts, the trace elements cycling through the system that provide the chemical diversity necessary for complex biological reactions to develop and sustain themselves. Europa's ocean, by this reading, may not simply be wet. It may be chemically fertile. Perhaps the most tantalizing element of Europa's potential habitability is what may exist at the bottom of that ocean, pressed against the rocky seafloor in the crushing darkness, more than 100 kilometers beneath the ice. If tidal heating is sufficient to maintain the ocean itself, it may also be sufficient to drive hydrothermal activity at the ocean floor. The same kind of geological venting that, on Earth, gave rise to the chemosynthetic ecosystems described around deep-sea vents. If the rocky seafloor of Europa is in contact with warm, chemically active water, and if that contact produces the kind of mineral-rich hydrothermal circulation observed at Earth's vent systems, then the floor of Europa's ocean may be precisely the kind of environment where, on Earth, life is known to originate and thrive. Scientists cannot yet confirm this. No spacecraft has reached the ocean floor. But the theoretical case for hydrothermal activity on Europa's seafloor is strong enough that it has become one of the central assumptions in the planning of future missions to the Moon. Then, in 2012, something happened that shifted the conversation in an unexpected direction. The Hubble Space Telescope captured evidence of what appeared to be water vapor plumes erupting from Europa's south polar region. Columns of water and ice particles being ejected from the surface into space, reaching heights of up to 200 kilometers above the Moon. If confirmed, these plumes would represent a direct pathway from Europa's subsurface ocean to the environment of space, a natural venting mechanism that brings ocean material to the surface without requiring any drilling or physical intrusion. Subsequent observations have produced additional evidence for plume activity, though the phenomenon appears to be intermittent and the data remains the subject of active scientific debate. What is not debated is the implication. If Europa is venting ocean material into space, a spacecraft passing through those plumes could potentially sample the chemistry of the subsurface ocean directly, tasting the contents of an alien sea from orbit without ever needing to touch the ice. This possibility has reshaped the priorities of planetary scientists considerably. Drilling through Europa's ice crust, estimated to be anywhere between 10 and 30 kilometers thick, represents an engineering challenge of staggering proportions with current and near-future technology. A mission capable of penetrating that much ice, surviving the journey to the ocean below, and then operating autonomously in the dark water beneath, lies well beyond anything humanity has yet built. But sampling a plume is a different proposition entirely. It requires only that a spacecraft be placed on a trajectory that carries it through the erupting column of material, equipped with the right instruments to analyze what it encounters. Europa Clipper, NASA's mission launched in October 2024, is designed to conduct close flybys of Europa and examine its surface, subsurface, and any plume activity in detail. It will not land, it will not drill, but it will look harder and more precisely at Europa than anything humanity has sent before. What Europa Clipper and future missions are ultimately looking for is biosignatures, chemical signals that would indicate biological activity. The presence of complex organic molecules in specific configurations, anomalous ratios of isotopes that chemistry alone cannot easily explain, evidence of metabolic byproducts, the molecular exhaust of organisms feeding on chemical energy in a dark ocean. None of these signals are guaranteed to be present, and their detection would require instruments of extraordinary sensitivity. But the fact that scientists are designing missions around their search represents something significant. The scientific community's assessment that Europa is not merely a theoretical candidate for life, but a place worth checking. Not a long shot. A genuine possibility. It is worth pausing on what it would mean if that possibility proved correct. Life on Europa would not be life that shares a common ancestor with Earth organisms. It would not be a cousin or a descendant. It would be a second, entirely independent origin of biology. Proof that life is not a singular accident that happened once on one lucky planet, but a phenomenon that chemistry, given the right conditions, produces on its own terms. That single discovery would be, without exaggeration, the most significant scientific finding in the history of human civilization. It would permanently alter every field of inquiry that touches on the nature and meaning of living systems. Biology, philosophy, theology, cosmology. A microbe in a dark ocean beneath the ice of a frozen moon would tell us something about the universe that no telescope aimed at the stars, no matter how powerful, has ever been able to confirm. That we are not alone. And that life, wherever the conditions allow it, rises. Europa is not the only world that has offered this possibility. It was not even the first to produce direct physical evidence of it. That distinction belongs to a smaller, less imposing moon, one that surprised the entire scientific community by not merely hinting at a subsurface ocean, but actively spraying its contents into space for visiting spacecraft to find. There is a particular kind of scientific discovery that does not arrive gradually, building through incremental observation toward a slow consensus. It arrives suddenly, in a single moment of data return, and the people looking at the readouts understand immediately that the field they work in will never quite be the same again. The discovery of Enceladus's geysers was that kind of moment. Not a theoretical prediction confirmed after decades of patient waiting. Not a subtle signal teased from noise by sophisticated statistical analysis. A geyser, a visible, active, ongoing eruption of water from the surface of a moon that, by every prior assessment, should have been geologically dead. Enceladus is small. Among the dozens of moons orbiting Saturn, it barely registers in terms of scale. Roughly 500 kilometers in diameter, a fraction of the size of Europa, small enough that it would fit comfortably within the borders of several mid-sized countries on Earth. Its surface is one of the most reflective in the solar system, a bright white shell of ice that bounces nearly all the sunlight that reaches it back into space, giving the moon a pristine, almost artificial appearance from a distance. Before the Cassini mission arrived in the Saturnian system in 2004, the scientific consensus on Enceladus was not particularly controversial. It is considered a frozen, inactive body, geologically quiet, surfaced in ancient ice, chemically unremarkable. A small moon doing nothing in particular in the cold outer reaches of the solar system. This assessment was not unreasonable. It was simply, as would soon become apparent, completely wrong. Cassini's early flybys of Enceladus produced data that initially puzzled mission scientists. The moon was warmer than it should have been. Not dramatically so, not in a way that was immediately obvious, but measurably, consistently warmer than models of a geologically inactive body at that distance from the sun could account for. The surface near the South Pole showed unusual thermal readings, and then the imaging data came back, and the puzzlement resolved instantly into something far more urgent. Near the South Pole of Enceladus, running along a series of long parallel fractures in the ice that mission scientists quickly named the tiger stripes, enormous plumes of water vapor and ice particles were erupting into space. Not vapor rising gently from a warm surface, Geysers, powerful continuous jets of material being driven upward from the interior of the moon and ejected at velocities sufficient to carry them hundreds of kilometers above the surface, out through the thin gravitational grip of a small moon, and into the space around Saturn. The discovery was announced in 2006, and it immediately elevated Enceladus from a minor footnote in the catalog of Saturnian moons to one of the most scientifically significant bodies in the solar system. The geysers were not a surface phenomenon. The energy required to sustain them, the volume of material they were ejecting, and the consistency of their activity all pointed unmistakably to a deep reservoir of liquid water beneath the ice. A subsurface ocean, like the one suspected beneath Europa's crust, but with one crucial and unprecedented difference. This ocean was not merely suspected, it was actively communicating with the surface. Material from the ocean interior was being driven upward through fractures in the ice shell and ejected directly into space, where a spacecraft was waiting. Cassini's mission team recognized immediately what this meant. They redirected the spacecraft. Rather than maintaining a safe observational distance, they flew Cassini directly through the Plumes. A decision that, in hindsight, stands as one of the most consequential maneuvers in the history of planetary exploration. In 2008, and again in subsequent flybys, Cassini passed through the erupting columns of material from Enceladus's interior, instruments running, collecting and analyzing everything it encountered. What it found went considerably further than water vapor and ice particles. The mass spectrometer aboard Cassini detected organic molecules in the plume material, carbon-bearing compounds, the molecular raw material from which the chemistry of life is built. This alone was significant. Organic molecules are not exclusively biological in origin. They form through purely chemical processes and are found throughout the solar system in comets, asteroids, and interplanetary dust. Their presence in Enceladus's plumes did not confirm life, but it confirmed that the ocean beneath the ice was not a simple, chemically inert pool of water. It was an active chemical environment, producing and circulating complex carbon-containing compounds. The ocean of Enceladus had chemistry. Interesting chemistry. Then came the hydrogen. In 2017, scientists analyzing data from Cassini's final close flybys of Enceladus announced the detection of molecular hydrogen, H2, in significant concentrations within the plume material. This finding attracted immediate and intense attention, not because hydrogen is unusual, but because of what its presence in those concentrations most plausibly implied about its origin. Molecular hydrogen in the quantities detected cannot be easily accounted for by surface processes or by the simple chemistry of cold ocean water. The most consistent explanation, the explanation that matched not just the hydrogen data, but the broader chemical and thermal profile of Enceladus, was hydrothermal activity at the ocean floor. Hot water, heated by geological processes in the rocky interior of the moon, reacting with the seafloor minerals in a process called serpentinization. Water interacting with iron and magnesium-rich rock, producing hydrogen as a chemical byproduct. The same process that, on Earth, fuels some of the most biologically productive hydrothermal vent environments ever discovered. If this interpretation is correct, and the Cassini science team presented it as the most parsimonious explanation for the data, not a speculative hypothesis, then the floor of Enceladus's ocean is not cold, dark, and chemically stagnant. It is warm. It is geologically active. It is producing hydrogen through mineral water reactions that, on Earth, provide the energy source for entire chemosynthetic ecosystems. The three requirements for life that the deep-sea vent discoveries on Earth made explicit, liquid water, chemical energy, essential elements, appear to be present simultaneously in the subsurface ocean of a moon orbiting Saturn. Not theoretically present, measured. Detected by instruments aboard a spacecraft that flew through the ocean's own exhaled material. The implications pressed uncomfortably against the boundary between scientific caution and scientific excitement. Mission scientists were careful, as they are trained to be, to avoid the word that every science journalist in the world immediately wanted to print. Life. They did not say that Cassini had found life in Enceladus's ocean. They said it had found conditions consistent with habitability. An environment where, if life were present, it would have the ingredients it requires to survive. This is a meaningful and important distinction in scientific practice, but it is also, when considered honestly, an almost impossibly enticing one. Conditions consistent with habitability on Earth are not theoretical. They are biological. They are places where life does not merely survive but proliferates. And those conditions appear to exist right now in an active and ongoing state inside a moon in our own solar system. There is another dimension to the Enceladus story that receives less attention than the chemistry, but deserves equal consideration: the timescale. How long has Enceladus been geologically active? How long has its ocean been liquid? How long have hydrothermal reactions been occurring at its seafloor? These questions are difficult to answer with precision, and the answers that scientists have proposed cover a range, from tens of millions of years to billions. If Enceladus's ocean has been liquid for hundreds of millions of years, that is a long time by any human measure, but perhaps not long enough for the kind of chemical evolution that preceded life on Earth. If it has been liquid for billions of years, the timeline aligns more comfortably with what we know about the emergence of terrestrial life. The uncertainty is genuine, and it matters. But even the lower estimates describe an ocean that has had more time to develop complex chemistry than any laboratory experiment humanity has ever run. What Cassini could not do, what its instruments, extraordinary as they were not designed to achieve, was definitively detect biological activity. The mass spectrometer that identified organic molecules and molecular hydrogen was built to characterize the chemistry of the plume material at a broad level. It was not optimized to distinguish between organic compounds produced by abiotic chemical processes and those produced by metabolic activity in living organisms. The biosignatures of life, if they were present in the plume material Cassini sampled, may have been there, and the instrument may simply not have had the resolution or the specificity to recognize them. This is not a criticism of the mission. It is a description of the next step. Cassini told us what to look for. It told us where to look. It handed future mission designers a target, a methodology, and a set of chemical questions that the right instrument sent back to Enceladus could potentially answer. The scientific community has been listening. Multiple proposed mission concepts aimed at Enceladus have been developed in the years since Cassini's plume discoveries. Some focus on plume sampling with more sophisticated mass spectrometry capable of detecting specific biosignatures. The molecular ratios, isotopic signatures, and structural complexity that would distinguish biologically produced compounds from abiotic ones. Others propose longer-term orbital observation, mapping the distribution and variability of the geysers to understand the dynamics of the ocean driving them. The logistical and financial challenges of such missions are real and significant. But the scientific case for returning to Enceladus is arguably stronger than for any other target in the solar system, precisely because the moon has already demonstrated its willingness to share. It is already venting its interior into space. Humanity has already, in a literal and unprecedented sense, flown through the exhaled breath of an alien ocean. The question of what lives in that ocean, whether anything lives in it at all, is one that the next generation of spacecraft may be equipped to answer. It is worth sitting with the strangeness of that for a moment. At some point in the early 21st century, a spacecraft built by human beings launched from a planet orbiting a medium-sized star in an ordinary spiral galaxy crossed the outer solar system and flew through material ejected from beneath the frozen surface of a moon orbiting Saturn. The instruments aboard that spacecraft detected water, organic molecules, and molecular hydrogen, the signature of geochemical processes that, on Earth, create the conditions for life. Humanity may have already sampled an alien ocean, may have already touched, however briefly and instrumentally, the interior of a world where something could be alive, and not known it because the tools required to recognize that life were not yet aboard. The ocean of Enceladus is not the only one waiting, but it is, at this moment, the one that has come closest to meeting us halfway. There is a moment when examining the data returned from Titan, when the familiar categories of planetary science begin to feel inadequate. Not because the data is unclear or the measurements imprecise, but because what they describe is a world that operates according to rules that are simultaneously recognizable and deeply disorienting alien. Titan is not a barren rock. It is not a frozen shell of ice. It is not a cratered wasteland or a volcanic hellscape. It is a world with weather. A world with rivers and lakes and seasonal cycles, with clouds forming in its atmosphere and precipitation falling from them onto a landscape shaped by erosion and deposition over geological timescales. By the standards of planetary complexity, Titan is extraordinary. And then you learn what its rivers are made of, and the familiar categories dissolve entirely. Saturn's largest moon was known for most of the history of telescopic astronomy as little more than a dot with an unusual spectral signature. It was Voyager 1, passing through the Saturnian system in 1980, that first revealed Titan's atmosphere in meaningful detail. A dense, opaque orange haze that completely obscured the surface from view. Thicker than Earth's atmosphere in terms of surface pressure, composed primarily of nitrogen with significant quantities of methane, and a complex photochemical smog of organic compounds in the upper layers. The atmosphere alone was striking. No other moon in the solar system has one remotely comparable. But what lay beneath that orange veil remained hidden until 2005, when the Huygens probe, carried to Saturn by the Cassini spacecraft and released to descend through Titan's atmosphere, transmitted images from the surface for the first time in history. What those images revealed sent scientists reaching for new language to describe what they were looking at. The surface of Titan is sculpted by processes that, on Earth, would be entirely familiar, if the medium involved were different. There are channels cut by flowing liquid, branching drainage networks that feed into wider basins. There are shorelines and delta formations. There are vast flat plains that appear to have been deposited by sediment-carrying flows. In the polar regions, the Cassini radar instruments mapped large bodies of liquid. Lakes and seas covering areas comparable to some of Earth's Great Lake systems. The northern polar region contains Kraken Mare, a body of liquid so large it would qualify as a significant sea on Earth, covering an area greater than the Caspian Sea. The geological vocabulary of rivers, deltas, erosion, sedimentation, and coastal geography all applies directly to Titan. Except that the liquid doing all of this is not water, it is methane and ethane, and a mixture of other short-chain hydrocarbons that exist in liquid form at Titan's surface temperature of approximately negative 179 degrees Celsius. Temperatures at which water is a rigid mineral, locked in the bedrock, as geologically inert as granite. On Titan, water ice plays the structural role that silicate rock plays on Earth. It forms a solid substrate beneath the surface. It is a building material, not a fluid. The fluid, the medium that fills the lakes, flows through the rivers, evaporates into the atmosphere, condenses into clouds and falls as rain on the landscape below, is liquid methane and ethane, cycling through a hydrological system that mirrors Earth's water cycle in every structural respect, while differing from it in almost every chemical one. Methane evaporates from the surface. It rises into the atmosphere, where photochemical reactions driven by filtered sunlight transform some of it into more complex organic compounds that contribute to the orange haze. It condenses in clouds. It falls as rain. It collects in lakes and rivers and flows back toward the seas. A complete planet-scale chemical cycle, operating entirely without water, in temperatures that would freeze any Earth organism solid within moments of exposure. The atmosphere adds another layer of complexity. Titan's photochemical smog is not simply pollution or interference. It is a continuously operating organic chemistry laboratory at planetary scale. Sunlight interacting with nitrogen and methane in the upper atmosphere drives the synthesis of a vast range of organic compounds. Tholins, scientists call them, a catch-all term for the complex polymer-like substances produced by high-energy irradiation of nitrogen-methane gas mixtures. These tholins settle through the atmosphere and coat the surface in a reddish-brown organic sediment, accumulating over billions of years into potentially deep deposits of complex carbon chemistry. Titan may have more organic material on its surface and in its atmosphere than exists anywhere else in the solar system. It is, in the most literal chemical sense, an organic world, a world bathed in the raw molecular ingredients of chemistry, building complexity through natural processes at a scale and duration that Earth's own prebiotic chemistry may never have approached. This is where the question of life on Titan becomes genuinely strange and genuinely interesting. Life on Earth is water-based. Its chemistry depends on liquid water as the solvent in which molecular interactions occur, in which membranes form and maintain themselves, in which genetic material replicates and metabolic reactions proceed. Water is not merely a convenient medium for Earth life. It is integrated into the fundamental architecture of terrestrial biochemistry at every level. The question of life on Titan cannot assume that same architecture. If life exists in Titan's methane seas, it would necessarily be life built around a different solvent, operating through different chemical pathways, structured according to different molecular principles. It would not be life as we know it. It would be life as we don't. A second independent experiment in biology, running on alien chemistry under alien skies. Theoretical biologists and chemists have considered what such life might look like, at least in outline. A methane-based organism would need cell membranes that function in liquid methane rather than liquid water, and in 2015, researchers at Cornell University published a computational study demonstrating that certain nitrogen-containing compounds could theoretically form stable, flexible membranes in liquid methane at Titan temperatures. They called the proposed structure an azotosome, a membrane formed not from phospholipids as in Earth cells, but from acrylonitrile, a compound that has since been detected in Titan's atmosphere by radio telescope observations. The study was theoretical. It was not a detection of life or even of life's precursors in assembled form. But it demonstrated that the chemistry necessary for one of the fundamental structural requirements of cellular life is not obviously forbidden by the conditions on Titan. The building blocks, at least in principle, are present. Energy is a more difficult question. Earth's methane-based analogy breaks down quickly when you ask what a Titan organism would metabolize. In the absence of oxygen and sunlight at the surface level, and in the absence of the thermal energy gradients that drive chemosynthesis at deep-sea vents, the energy budget for surface life on Titan is constrained. Some researchers have proposed that hypothetical Titan organisms could metabolize hydrogen, reacting it with acetylene, a compound produced in the atmosphere and deposited on the surface, to release energy in a process that produces methane as a byproduct. This pathway would have a detectable surface signature, a depletion of atmospheric hydrogen near the surface, and an anomalous absence of acetylene in surface deposits. Data from Cassini has been interpreted by some scientists as showing exactly these patterns, though the observations are ambiguous and the chemical explanations multiply quickly. No single reading of the data compels a biological interpretation, but the patterns are interesting enough that they have not been dismissed. Beneath the surface, Titan presents an entirely separate and perhaps more conventionally promising habitat. Models of Titan's interior suggest that beneath the outer ice shell, the moon may harbor a subsurface ocean of liquid water, not the hydrocarbon seas of the surface, but a water-ammonia mixture maintained in liquid state by the combination of radiogenic heat from the rocky core and the antifreeze properties of dissolved ammonia. If this internal ocean exists, it would resemble, in its broad chemical environment, the subsurface oceans of Europa and Enceladus more closely than it resembles the methane lakes above. It would be cold, dark, and removed from the organic chemistry of the surface by kilometers of ice. But it would be liquid water with dissolved minerals and potentially enough chemical energy to support the kind of microbial life that the deep-sea vent discoveries on Earth have demonstrated can thrive in similar conditions. Titan therefore offers something that no other world in the solar system can match. Two independent potential habitats for life, operating under entirely different chemical regimes, stacked one above the other on the same body. A surface environment of exotic hydrocarbon chemistry, with organic compounds accumulating over billions of years and a complete global chemical cycle. And a subsurface environment of liquid water, chemically more familiar, thermally driven by internal geology. Whether either of these environments hosts life is unknown. Whether both could do so simultaneously is a question that current science cannot begin to resolve. But the structure of the problem itself, two distinct habitability scenarios on a single world, represents a complexity that the simple Goldilocks model of planetary habitability was never designed to accommodate. The Dragonfly mission, currently developed by NASA and targeting a launch in the late 2020s, with arrival at Titan in the 2030s, will deploy a rotorcraft lander to fly across Titan's surface. an aerial vehicle capable of covering distances that no previous planetary lander has managed, sampling chemistry at multiple sites and building the most detailed picture of Titan's surface environment ever assembled. It will not drill to the subsurface ocean. It will not sample the methane seas directly, but it will examine the organic chemistry of the surface in detail, fine enough to look for patterns, distributions of molecules, isotopic ratios, structural complexities that might distinguish purely abiotic chemistry from something more. It will ask, with instruments of unprecedented sensitivity, whether the organic world of Titan is simply a very interesting chemistry experiment, or whether it has, somewhere in its 4 billion-year history, crossed the threshold into biology. Titan is, in this sense, a different kind of challenge than Europa or Enceladus. Those worlds ask whether familiar life, microbial, chemosynthetic, water-dependent, might exist in conditions analogous to Earth's deep sea. Titan asks something harder and stranger, whether life can exist at all in conditions that have no analog anywhere on Earth, running on chemistry that terrestrial biology never developed, using a solvent that freezes long before it reaches the temperatures at which any known organism can function. It asks whether life is a universal property of chemistry under the right conditions, or whether it is a specific solution to a specific set of problems that happens to work in liquid water and nowhere else. The answer to that question would not merely tell us whether Titan is inhabited. It would tell us something fundamental about what life is, and how far the universe is willing to go to produce it. That question will not be answered quickly, but it has already been asked by every image of a methane river carving through an orange landscape under a pale, distant sun. For most of the 20th century, the solar system was understood as a collection of rocky planets, gas giants, and largely inert moons. A neighborhood whose broad features had been mapped and whose fundamental character was, if not fully known, at least reasonably well constrained. Life in this framework was an Earth problem, a singular event on a singular world surrounded by geologically dead or chemically sterile bodies that served as interesting objects of study but not as serious candidates for biology. The discoveries at Europa and Enceladus disturbed this picture significantly. But they could still, if one was inclined toward caution, be treated as exceptions. Unusual cases produced by unusual circumstances. Gravitational accidents of proximity to gas giants, massive enough to generate the tidal heating that liquid water requires. 2 ocean worlds in one solar system was surprising. It was not yet a pattern. The pattern emerged gradually as mission data accumulated and planetary scientists began applying improved models of interior heating, ice mechanics, and gravitational dynamics to the full catalog of moons and dwarf planets orbiting the Sun. What they found, world by world, was that Europa and Enceladus were not anomalies. They were examples of something far more common than anyone had anticipated. Subsurface liquid water, it began to appear, is not a rare and improbable feature of a few specially positioned moons. It may be one of the most widespread conditions in the outer solar system, a product of physical processes so general and so persistent that almost any sufficiently large icy body, given enough time and the right interior composition, may develop and maintain a liquid layer beneath its frozen outer shell. Ganymede is the largest moon in the solar system, larger than the planet Mercury, large enough that if it orbited the Sun directly rather than Jupiter, it would be classified as a planet without controversy. For most of its observational history, Ganymede was known primarily for its size and its unusual surface geology, a mixture of ancient dark terrain and younger, grooved bright terrain that indicated a complex geological past. Then, in 2015, the Hubble Space Telescope detected something in Ganymede's auroral activity. Subtle oscillations in the Moon's auroral bands, caused by the interaction between its own magnetic field and Jupiter's, that provided the clearest evidence yet for a subsurface ocean. The oscillations were smaller than expected, dampened in a way that matched models of a highly conductive layer beneath the ice disrupting the magnetic field interaction. Salt water. A global subsurface ocean of salt water, estimated to be approximately 800 kilometers deep. So deep that it dwarfs any ocean on Earth by a factor that requires a moment to absorb. 800 kilometers of liquid water beneath the surface of a moon. A body of ocean so vast that its volume may exceed the total water content of Earth by an enormous margin. The Galileo spacecraft had previously found magnetic field evidence consistent with this conclusion. But the Hubble auroral measurements provided the most compelling confirmation. What Ganymede's ocean means for habitability is less clear than in the cases of Europa or Enceladus. The ocean is believed to be sandwiched not between ice above and rock below, but between layers of ice. High-pressure ice phases at the bottom, formed under the crushing weight of the ocean above, separating the liquid layer from the rocky interior. This is significant because direct contact between liquid water and rock is what enables the mineral exchange and chemical reactions that, on Earth, drive hydrothermal activity and support chemosynthetic ecosystems. If Ganymede's ocean floor is ice rather than rock, the chemical energy available to any potential biology may be considerably more limited than in Europa or Enceladus, where the ocean-rock interface appears to exist and to be active. Ganymede's ocean may be vast, like one of the largest bodies of liquid water in the solar system, and yet, by the strange logic of astrobiology, potentially less chemically interesting than the much smaller ocean of Enceladus. Size in this context is less important than interface. The question is not how much water a world has. It is what that water is touching and what chemistry those contacts are driving. Callisto, the outermost of Jupiter's 4 large Galilean moons, presents a different and in some ways even more puzzling case. Callisto's surface is the most heavily cratered terrain in the solar system. An ancient, battered landscape that has preserved its impact record across billions of years, suggesting a geologically inactive interior that has done nothing to resurface or erase the record of ancient bombardment. By almost every measure, Callisto appears to be a dead world. Its interior shows no signs of the differentiation, the separation of rocky and icy components into distinct layers, that characterizes geologically active bodies. And yet the Galileo spacecraft's measurements of Callisto's magnetic response to Jupiter's field produced results that scientists struggled to explain without invoking a layer of electrically conductive material beneath the surface. The simplest explanation, as with Ganymede, was a subsurface ocean of liquid salt water. A geologically dead moon, ancient and battered and apparently inert, may nonetheless contain a global ocean somewhere beneath its cratered exterior. How it maintains that ocean without obvious internal heat sources remains a question that planetary models have not fully resolved. But the magnetic data has not gone away, and neither has the conclusion it most naturally supports. Beyond the Jovian system, The inventory of suspected ocean worlds continues. Triton, Neptune's largest moon and one of the most geologically unusual bodies in the solar system, has attracted renewed attention in the context of subsurface oceans. Triton orbits Neptune in a retrograde direction, opposite to the planet's rotation, a strong indication that it was not formed alongside Neptune, but was captured from the outer solar system at some point in the distant past. This capture would have subjected Triton to enormous tidal stresses during the circularization of its orbit, a process that generated substantial internal heat and may have maintained a subsurface ocean for hundreds of millions of years following capture. Whether that ocean persists today depends on how quickly the tidal heating dissipated and how much residual radiogenic heat Triton's interior generates. Triton also displays active geological features. Nitrogen geysers observed by Voyager 2 during its 1989 flyby, suggesting that the moon's interior remains at least partially active. It is by most assessments a serious candidate for a subsurface ocean, though far less studied than the Jovian and Saturnian moons and considerably more difficult to reach. And then there is Pluto, the former ninth planet, reclassified as a dwarf planet in 2006, and subsequently dismissed in some quarters as a diminished and geologically uninteresting body, received its first close examination in 2015, when the New Horizons spacecraft made its historic flyby. The images and data it returned defied almost every expectation. Pluto's surface displayed enormous geological variety. Mountain ranges of water ice, rising kilometers above the plains. Vast nitrogen ice sheets, slowly convecting in patterns driven by internal heat. And a heart-shaped basin of extraordinary size and youth that indicated active resurfacing within geologically recent timescales. A body at the outer edge of the solar system, receiving almost no sunlight and with no large neighboring planet to provide tidal heating, was geologically active. The heat driving this activity must be internal. Radiogenic decay from elements within Pluto's rocky core, releasing energy slowly but persistently over billions of years. If that heat is sufficient to drive the surface activity New Horizons observed, it may also be sufficient to maintain a liquid water layer beneath the ice. Preliminary modeling based on the New Horizons data suggested that a subsurface ocean is plausible and possibly likely, a conclusion that would have seemed almost absurd before the flyby and now sits within the mainstream of planetary science discussion. What all of these discoveries collectively describe is something that planetary scientists are only beginning to fully articulate. Ocean worlds may be the norm in the outer solar system, rather than the exception. The conditions that produce subsurface liquid water, a combination of radiogenic internal heat, tidal stress from nearby massive bodies, antifreeze compounds like ammonia dissolved in the water, and the insulating properties of thick ice crusts, are not rare coincidences requiring a specific and improbable chain of events. They are products of general physical and chemical processes that apply broadly across a wide range of icy bodies of sufficient size. If this is true of our solar system, it is likely true of planetary systems throughout the galaxy. Every star that forms giant planets likely forms icy moons alongside them. Every icy moon above a certain size threshold is a candidate for interior liquid water. The galaxy may contain not hundreds or thousands but billions of subsurface oceans, vast, dark, chemically active bodies of liquid water, distributed across the cosmos in numbers that make the head swim. This recasting of the solar system From a mostly dry, mostly frozen collection of barren worlds with one inhabited exception, to a system rich in liquid water habitats stacked beneath ice across dozens of bodies, does not guarantee that life is common. Liquid water is a necessary condition, not a sufficient one. The gap between a chemically interesting ocean and a biologically inhabited one remains real and scientifically unresolved. But the probability calculus changes dramatically when the number of candidate habitats expands from one to potentially dozens within a single solar system, and from dozens to billions when extended across the galaxy. Life on Earth did not require exceptional conditions. It required liquid water, chemical energy, and time. The universe, it is increasingly clear, has been distributing all three with a generosity that no one quite expected. What it has done with them, whether it has done anything at all with them in the dark oceans of all those frozen worlds, remains the question that defines the next century of exploration. The question of whether life exists beyond Earth has occupied human thought for centuries. In philosophy, in theology, in science fiction, and eventually in science itself. For most of that time, it remained purely theoretical, a question without a methodology, an inquiry without an instrument. The tools required to move it from speculation into empirical investigation simply did not exist. And so the question sat at the edge of what science could reach, fascinating and unresolved, generation after generation. That era is ending. Not metaphorically, not as a rhetorical gesture toward optimism, but literally, mechanically, in the form of spacecraft already built or under construction, missions already funded or in advanced planning, instruments already designed and tested and pointed toward the worlds that the last 3 decades of discovery have identified as the most promising places to look. The search for alien life is no longer a philosophical exercise. It is an operational one. Europa Clipper represents the most immediate and most direct expression of that shift. Launched in October 2024 aboard a SpaceX Falcon Heavy rocket, the spacecraft is currently in transit to the Jovian system, scheduled to enter orbit around Jupiter in 2030. It will not land on Europa. It will not drill through the ice or deploy instruments into the ocean. But what it will do across nearly 50 close flybys of Europa conducted over several years is build a portrait of that moon more detailed and more scientifically complete than anything previously attempted. Its instrument suite, 9 scientific instruments in total, is designed specifically around the questions that 4 decades of remote observation have raised about Europa's subsurface ocean. A radar sounder will map the ice shell's thickness and internal structure, looking for regions where the ocean comes closest to the surface and identifying sites most favorable for future landers. A mass spectrometer will analyze the thin material scattered around Europa by micrometeorite impacts and by any plume activity the spacecraft encounters, searching for organic compounds and other chemical signatures. A magnetometer will refine measurements of Europa's magnetic field, tightening the constraints on the ocean's depth, salinity, and conductivity. Cameras will image the surface at resolutions that previous missions could not approach, documenting the geological features that betray the ocean's influence on the ice above. What Europa Clipper is ultimately doing is reconnaissance. Systematic, scientifically rigorous reconnaissance of a world that subsequent missions will need to land on and eventually penetrate. It is building the map that future engineers will use to select a landing site, understanding the environment that future landers will need to survive in, and identifying the chemical targets that future instruments will need to characterize in detail, sufficient to distinguish biology from abiotic chemistry. The mission is not designed to discover life. It is designed to determine where and how a mission capable of discovering life should go. That distinction is important because it reflects the genuine scale of the challenge ahead. Europa's ocean is not accessible from orbit, or from the surface, or from a lander sitting on the ice. It is accessible only from beneath the ice, and reaching it will require technological capabilities that humanity is still developing. The engineering problem of penetrating Europa's ice crust, estimated at anywhere between 10 and 30 kilometers of solid ice, in a radiation environment produced by Jupiter's magnetosphere that would destroy unprotected electronics within hours, has been the subject of serious research for decades. Multiple concepts have been proposed. Cryobots, cylindrical probes designed to melt their way through ice using embedded heating elements, have been developed and tested in Antarctic field conditions. Concepts for deploying tethered communication systems through the ice to maintain contact between a surface relay and a submerged probe have been studied at the systems level. None of these technologies are ready for deployment at Europa today, but they are advancing, and the scientific urgency created by Europa Clipper's expected findings is likely to accelerate that development considerably. The mission after Europa Clipper, the lander, the penetrator, the ocean probe, has not yet been formally approved or funded. But within the planetary science community, the trajectory of that program is already being mapped. While Europa Clipper advances toward Jupiter, a different and in some ways more immediately accessible target is being prepared for investigation. Dragonfly, NASA's rotorcraft lander mission to Titan, is currently scheduled for launch in 2028, with arrival at Titan in 2034. Its approach to the problem of searching for life is fundamentally different from anything previously attempted in planetary exploration. Rather than landing at a single site and conducting localized analysis, Dragonfly will fly, using Titan's dense atmosphere and low gravity to lift itself from site to site across the surface, covering distances of tens of kilometers per flight, and visiting multiple scientifically distinct locations over the course of its planned mission. This mobility changes the character of what is scientifically possible in a profound way. Previous landers and rovers have been constrained by the geology immediately surrounding their landing site, able to sample only what they could reach by slow surface travel across difficult terrain. Dragonfly will be able to select its targets from the air, navigate to them directly, and sample the chemistry of Titan's surface at a diversity of locations that would take a conventional rover years to reach, if it could reach them at all. The science Dragonfly is designed to do is focused on Titan's organic chemistry, the complex carbon compounds that accumulate on the surface through atmospheric photochemistry, and that represent collectively a 4 billion-year archive of prebiotic chemical evolution on a planetary scale. Among its target sites is the Selk impact crater, where an ancient asteroid impact would have melted the water ice that forms Titan's bedrock, creating a temporary liquid water environment in which the organic compounds from the surface mixed with the water from below. A brief, localized, potentially chemistry-rich event that some scientists have proposed as a plausible setting for prebiotic synthesis. If the organic compounds in that crater show signs of the kind of complexity and selectivity that characterize biological chemistry, specific molecular structures present in anomalous abundance, isotopic ratios inconsistent with purely abiotic synthesis. The implications would be difficult to contain within any cautious scientific framing. Enceladus, despite its arguably stronger immediate case for habitability, with its active plumes, confirmed organic chemistry, and molecular hydrogen pointing to hydrothermal activity, currently lacks an approved follow-up mission. The scientific community has advocated strongly for one. In the 2023 Planetary Science and Astrobiology Decadal Survey, the 10-year prioritization document produced by the National Academies of Sciences that guides NASA's mission planning, an Enceladus Orbilander mission was identified as a high-priority concept, a spacecraft capable of orbiting the Moon, flying through its plumes repeatedly with instruments more sophisticated than those carried by Cassini, and eventually landing near the tiger stripe fractures to sample material directly from the venting sites. The mission concept is technically feasible. Its scientific case is compelling. What it currently lacks is the formal approval and funding commitment that would move it from concept to hardware. Given the budget realities of large planetary missions and the long lead times involved in their development, an Enceladus Orbilander is likely a mission of the 2040s or 2050s at the earliest. But the scientific case for it grows stronger with every year of additional analysis applied to the Cassini dataset. What all of these missions share beyond their individual scientific objectives is a common and historically unprecedented ambition: to conduct for the first time in human history a systematic search for life in environments other than Earth, using instruments specifically designed to recognize it. Previous missions to Mars, to Titan, to the outer planets have searched for habitability, for the conditions that could support life, for the chemical building blocks from which life might be constructed. The missions now being built and planned are beginning to move beyond habitability and toward detection, toward the specific chemical and biological signatures that would distinguish a living environment from a merely chemistry-rich one. That shift in framing reflects the accumulation of evidence over the past 3 decades. When scientists did not know whether liquid water existed anywhere beyond Earth, searching for habitability was the necessary first step. Now that liquid water has been confirmed or strongly inferred in multiple locations within the solar system, the question has advanced. The environments exist. The question is what is in them. The timescale involved is worth considering honestly. Europa Clipper's primary mission runs through the mid-2030s. Dragonfly arrives at Titan in 2034 and conducts its surface operations across subsequent years. An Enceladus mission, if approved in the coming decade, would reach its target in the 2040s or 2050s. The discovery of biosignatures, if they exist, and if the instruments are capable of recognizing them, would likely not be a single announcement, but a gradual accumulation of evidence requiring years of analysis, replication, and debate before any consensus formed. Science does not produce revelations on a schedule. It produces data, and data requires interpretation, and interpretation requires time and scrutiny, and the slow, sometimes painful convergence of expert opinion across a community of people who are professionally trained to be skeptical of extraordinary claims. The discovery of alien life, if it comes, will almost certainly not arrive as a dramatic press conference moment. It will arrive as a growing weight of evidence that alternative explanations can no longer adequately bear. But the weight is already beginning to accumulate. not the weight of a confirmed detection. That has not happened. The weight of a narrowing gap between what we know and what we are able to find out. Every mission that has visited the outer solar system has returned data more interesting than the mission before it. Every probe that has passed through the Jovian or Saturnian system has found a solar system more chemically complex, more geologically active, and more biologically plausible than the one its predecessor described. The trajectory of that accumulation, extended forward across the next 3 decades, points toward a moment, not guaranteed but genuinely possible, when a spacecraft returns data from the ocean of Europa, or the plumes of Enceladus, or the organic plains of Titan, and the scientists analyzing it find themselves confronting evidence that the simplest, most parsimonious explanation is not chemistry. It is life. That moment has not arrived, but for the first time in the history of the question, the instruments capable of producing it are being built. There is a thought experiment that planetary scientists and astrobiologists return to with some regularity, not because it resolves anything, but because it clarifies the weight of what is at stake. Imagine that tomorrow a spacecraft returns data from the subsurface ocean of Europa. Organic compounds and configurations that abiotic chemistry cannot easily produce. Isotopic ratios that metabolism would explain more cleanly than geology. Molecular structures with the kind of asymmetric handedness that, on Earth, is a signature of biological selection rather than random chemical synthesis. Imagine the data is unambiguous. Imagine the scientific community, after months of analysis and vigorous debate, arrives at a consensus. The ocean of Europa contains life. Sit with that for a moment, not as a scientific result, but as a fact about the universe. A second origin of life. Biology arising independently from different chemistry, in a different ocean, under a different sky, or rather under no sky at all, beneath kilometers of ice in total darkness, with no knowledge that the rest of the cosmos exists. What does that mean? Not just for planetary science, not just for astrobiology, but for the broader human understanding of what life is, where it comes from, and what its existence in the universe signifies. The answer, considered carefully, is that it means almost everything. A single origin of life, one event on one planet, under one set of conditions, is consistent with life being a vanishingly improbable accident, a statistical outlier so extreme that its recurrence anywhere else in the universe would be unlikely to the point of impossibility. The history of Earth life in this reading is a singular event, the product of a chain of molecular coincidences so specific and so improbable that it will not happen again in any meaningful time frame. This interpretation has never been scientifically demonstrated, but it has never been disproven either. And it quietly underlies a great deal of human thinking about the specialness of Earth and the solitude of conscious life in the cosmos. A second origin of life discovered not across intergalactic distances but in our own solar system, on a moon we can reach with our own spacecraft, would not merely challenge this interpretation, it would shatter it irreparably. Two independent origins of life in a single solar system would mean that life is not an accident. It would mean that life is what chemistry does, given liquid water and energy and time and the right molecular building blocks. That it is an emergent property of matter under certain conditions, as inevitable in its way as the formation of crystals or the behavior of fluid dynamics. And if life emerges independently twice in the same solar system, in environments as different from each other as Europa's dark ocean is from the conditions that produce the first cell on Earth, then the implication extends outward without obvious limit. Every star in the galaxy that hosts planets or moons with liquid water and chemical energy becomes a candidate. Every icy moon orbiting every gas giant in every planetary system becomes a possible habitat. The galaxy, which contains somewhere between 200 and 400 billion stars, most of which appear to host planetary systems, most of which likely contain icy bodies in their outer reaches. That galaxy becomes, in this reading, a place saturated with life. Not intelligent life necessarily, not technological civilization, but life in its microbial and foundational forms, distributed across the cosmos in numbers that exceed any human intuition for large quantities. The philosophical consequence of that realization is difficult to articulate without it sounding like hyperbole, because the language available for describing it was developed in a cultural and intellectual context that assumed Earth's biology was unique. We do not have good words for the experience of discovering that life is a universal phenomenon, because no human being has ever had that experience. What we have are the words that the discovery would make inadequate. Words like rare, special, exceptional alone. And the negative space they would leave behind, waiting for new concepts to fill it. The history of science contains several moments when a discovery fundamentally restructured humanity's understanding of its position in the cosmos. The Copernican recognition that Earth orbits the Sun, not the reverse. The Darwinian recognition that humanity is not a separately created species, but a branch of a single tree of life connecting all organisms on Earth. The cosmological recognition in the 20th century that the Milky Way is not the universe, but one of hundreds of billions of galaxies in an observable cosmos of almost unimaginable scale. Each of these moments produced not just a scientific revision, but a philosophical one. A renegotiation of what it means to be human in relation to the rest of what exists. The discovery of life beyond Earth would be the next such moment, and by most assessments, the most significant of all. What makes this reflection more than philosophical abstraction is the specific character of the life that might be found. The organisms, if they exist, in the ocean of Europa or the vents of Enceladus, would almost certainly be microbial. Simple by the standards of complexity that multicellular life on Earth has achieved. They would not be aware of us. They would not be constructing civilization or transmitting signals or looking up through their ice ceiling and wondering whether something exists on the other side. They would be doing what the earliest life on Earth did, metabolizing chemicals, reproducing, evolving slowly in response to the pressures of their environment, building the kind of biological complexity that, given enough time and the right conditions, may or may not eventually produce something more. They would be, in the most fundamental sense, our equals in the only category that matters at the level of first discovery: alive. And in that equality, in the recognition that life had found a way in an ocean we had never seen, on a world we had dismissed as frozen and dead, something in the human understanding of the cosmos would change in a way that could not be undone. Beneath the ice of Europa, the water has been moving in the dark for billions of years. Beneath the fractured surface of Enceladus, an ocean warmed by the chemistry of rock and water has been venting its interior into space for long enough that the material it has ejected forms one of the rings of Saturn. Beneath the methane rain of Titan, organic compounds have been accumulating and reacting and building complexity across a timescale that dwarfs the entire history of human civilization by a factor so large it resists comprehension. These processes did not begin when we discovered them. They did not begin when we sent spacecraft to observe them. They have been proceeding quietly and without interruption for most of the history of the solar system, indifferent to our awareness, independent of our science, existing entirely on their own terms and environments that our instruments are only now beginning to reach. Whether life participates in those processes remains unknown. The honest scientific answer at this moment is that we do not know. We know the conditions, we know the chemistry. We know that on Earth, conditions far less promising than those of Europa or Enceladus have proven sufficient for life to arise and persist across billions of years. We know that the ingredients are present, that the energy is available, that the time has been sufficient. What we do not know, what no instrument yet built has been able to determine, is whether the step from chemistry to biology has occurred in any ocean beyond our own. That step, the origin of life, remains the deepest unsolved problem in all of science. We do not understand how it happened on Earth. We cannot yet predict the conditions under which it will happen elsewhere. We can only point to the environments where it might and go look. And so that is what humanity is preparing to do. Slowly, deliberately across the decades of exploration that lie ahead. Spacecraft are being built. Instruments are being calibrated. Trajectories are being calculated toward moons that harbor oceans older than any life on Earth. The question has been asked for long enough. The tools to begin answering it, imperfect and limited as they still are finally being assembled. Somewhere in the outer solar system, beneath ice that has never seen sunlight, in water that has never known a surface, something may be waiting. Not for us. Not with any awareness that we exist or that we are coming. Simply existing as life does, as life has always done, in the only way it knows. In the dark. In the deep. Patient as an ocean. Ancient as the ice above it,